Hello, my name is Vitalis Wiens and today I'm going to present our work on customizable chart visualizations of tabular data using knowledge graphs. In the age of digitalization, we are surrounded by data, and data comes in various formats, shapes, and from different knowledge domains. Semantic web technologies provide us with a machine-readable access to information using explicit semantics. Tabular data provides a compressed representation of information. The data is organized in rows and columns, and tables are still frequently used in different knowledge domains. The underlying information of tables can be aligned or used to populate and create knowledge graphs. The transformation of tables to knowledge graph representations is an ongoing research topic. However, in this work, we address the visualizations of tabular data originating from knowledge graph representations. Visualizations can support development, exploration, communication, and sense-making. Therefore, visualizations provide an abstraction of information that reinforces human cognition. However, different visualization methods and tools exist for different use cases. Suitable visualizations are highly dependent on the individual use case and also on the targeted user groups. As a use case, we present the Open Research Knowledge Graph. Scientific articles are typically published as PDF documents. Therefore, searching, understanding, and organizing information becomes a burden for the reader. The Open Research Knowledge Graph transforms findings and results of scientific articles into structured and machine-readable representations. Generally, the information in papers is presented using descriptive text, figures, and tables. In this work, we focus on tables because they provide an organized and compressed representation of information. Tables of scientific articles serve as an input for a pipeline-based approach. The data acquisition and transformation modules create a knowledge graph representation for the table. This information is organized and analyzed for the creation of chart visualizations. Additional user interactions provide means to customize the resulting representation. In this work, we address the following challenges. What minimal information structure is required in a knowledge graph to obtain visual representations of tabular data? How to analyze this structured information for visualization generation? Knowledge graph representations typically reflect a triple-based structure. In our approach, we use a simple transformation model where the cell entries of the first column provide the subjects. The header values of other columns provide the predicates, and their cell values provide the objects. Here we see a simple transformation for the first row of the table into such a triple-based representation. However, these triples just reflect data points with limited semantics. For information retrieval tasks, the structure and the semantics of the triples need to be known a priori. How can we tackle these challenges? With additional semantics. Our approach augments the tabular data with additional semantics using a human-in-the-loop approach. The additional semantics extend the cell values with metrics and units information. A widget ensures the correct assignment of additional semantics using a human-in-the-loop approach. A node link diagram visualization indicates the resulting structure in a knowledge graph. The table is organized using row nodes. In our example, a row node is assigned to a method. Row nodes are connected to cell nodes, where each cell node has its corresponding value and the information about the additional semantics. The additional semantics provide the context for the individual values. For example, the value 89 describes precision. It has the unit percentage, and it refers to a method, in this case method A. Using the known structure and the additional semantics, we can reconstruct tables from knowledge graphs that can be used to create chart visualizations. The reconstruction of a table enables us to create different views on the information using corresponding implementations. For example, we can order the columns in an ascending or descending order. These tables serve as input for chart visualizations. The additional semantics provide guidance for the creation of meaningful visualizations. For example, visualizing runtime and F1 score in one chart does not provide a meaningful representation of the information. It is simply due to the large differences in value ranges. Units provide reasonable candidates to organize the information in subtables. Similar units provide us with information that metrics relate or correlate to each other. Therefore, these could be visualized in one chart. As an example, we can see the chart visualization for the subtable for the unit percentage. Additional customizations allow us to organize the information based on the metrics, showing us the performance of individual methods or how individual methods performed in each metric. The analysis of units allow us to create uniform representation of cell values. For example, the string representation of 89% or 0.89 is converted to just 89, since the unit is already provided as additional semantic of the cell value. Furthermore, these semantics allow us to define rules in order to align compatible units. For example, converting milliseconds to seconds. Using the semantics and the rules, we can detect information of related columns. For example, merging subtables for compatible units such as seconds and milliseconds. While units provide reasonable mappings, identical units are often used to describe different metrics. For example, the F1 score is a performance measurement described in percentage, which differs from a statistical distribution where the values of a column should sum up to 100%. In order to address this challenge, we use the semantics of metrics. These define compatible visualization methods for individual metrics and thus reduce the visualization space for the data at hand to only meaningful representations. For example, pie charts and box plots are not suitable to represent F1 score, recall, or precision. Furthermore, the semantics of metrics enable validation mechanisms. For example, runtime cannot be a negative number. Percentage for the metrics in our example should be in the range between 0 and 100, and more, the pH value used in descriptions of chemical materials should be in the correct range. Here we see an implementation for a possible user workflow. On the left side, the user is provided with the reconstructed table, allowing to investigate the data and get an overview. In the middle, we have the selection window that allows the user to see the data that has been organized based on the units. And on the right, we have the customization window. It provides the applicable chart visualization methods for the selected subtable and additional options to adjust the final result. As a rendering engine, we use Google Charts, and it is controlled by a user interface to enable customizations. As a prototype, our approach has several limitations. We use a simple structure for the transformation model. We currently support only one-dimensional cell values. Furthermore, sorted entries such as time series are not supported by the implementation. The analysis of semantics is realized using string comparisons and ad hoc rules. Furthermore, the approach requires user input to assign units to columns. Suitable visualization methods and the metrics are defined for our input example. A myriad of metrics needs to be defined first. The visualizations are limited with respect to the implementation. It is a set of supported visualization methods and the customization options. Using the comparison feature of Open Research Knowledge Graph, we can create visualizations for the information across different papers. The information of all tables is analyzed and subgroups of tables are created based on their units. The transformation rules enable us to align the different numerical values to a uniform representation, as seen in the last table. Furthermore, we can create leaderboard visualization for the papers. For example, we select the metric runtime and adjust the performance operator to the minimum. In summary, Our approach uses a simple information structure to transform tables to knowledge graph representations. Additional semantics for metrics and units enable us to analyze the data for the generation of suitable visualizations. With that, I would like to conclude. Answer your questions. I will.